Okay, so for question 4, we're looking at learning objectives 3 and 4, which is describe the experiments to show the force on the current carrying conductor and magnetic field, including to show the force, right? So this is the motor effect experiment to show the effect of reversing the current and the direction of the field. Okay, that's why I kept emphasizing, asking you what happens if you reverse the current, what happens if you reverse the field, right? So this is in your syllabus. The other thing is deduce the relative directions of force, field, and current when any of these two quantities are at right angles to each other using Fleming's left-hand rule. So you need to use Fleming's left-hand rule to decide what will happen. Okay, so these are the things that are in your syllabus you're expected to know. Let's do question 4. Okay. So the diagram shows a wire placed between two magnetic poles. State what will happen when the current in the wire flows from A to B. Okay, please go and use Fleming's left-hand rule to see if you understand how to use it. Force, field, current. Pause the video to try yourself first. Okay, pause the video to try yourself. Okay, force, field, current. Let's say current is going A to B. Current is going into the page. Field is going north to south. Field is going north to south. Force, field, current. So current, field is going north to south. So what happens? The wire will experience a force downwards and hence will deflect downwards. Okay? So the wire will experience a force downwards and hence deflect downwards. Okay? Now, part B, what if the current goes from B to A? So now my current is going from B to A. My field is still north to south. So force, field, current. Current goes from B to A, middle finger. Field left to right, my force is upwards. Of course, you also have known that if you did the first one correctly, you change the direction of current, my force will be opposite, will flip also. Okay, so now the wire will experience a force upwards and hence deflect downwards. Okay, if let's say they ask you to state and explain, okay, which I actually will cover in the next lesson. All you need to say is that a current carrying conductor placed in a magnetic field will experience a force with its direction given by Fleming's left-hand rule. Okay, so you just need to state, when they ask you to explain, you just need to say that because the current carrying conductor is placed in an external magnetic field, when that happens, it will experience a force, and that force, the direction of that force can be given by Fleming's left-hand rule. Yeah, that's the explain part. But for now, state is what I want you to get. Okay, I hope the background noise is not too noisy. And with that, we've actually come to the end of this lesson. What happens to the current carrying conductor when I place it into an external magnetic field? It will experience a force. What happens when you reverse the direction of the current magnetic field? When you reverse the current, the force will flip. You reverse the magnetic field. Yeah, so if you reverse the current, the force will flip, will be reversed as well. You reverse magnetic field, the force also reverse. Okay, of course, if you reverse both, then you reverse, then you will not reverse. Just use Fleming's left-hand rule. Okay, and yeah, how can I determine the relative directions of these quantities? Fleming left-hand rule. All right. So I hope you've managed to follow on in this lesson. Challenge yourself. Here's a question for you. If a positively charged particle, a positively charged particle moves into a magnetic field like this, okay? So magnetic field is the axis by convention, so it means the same thing. The magnetic field is pointing into the paper, okay? So now this is not current, now this is magnetic field, okay? So all of these are magnetic fields. All the magnetic fields are pointing into the paper. This is a positive charge that is moving in like this. What will happen to its direction? What will be the direction of the particle? Explain your answer. Okay? So pause the video to give yourself a think. So this requires you to put together what you've learned, right? If a positive charge is moving in, then which direction is your current? Remember, by convention, conventional current is a direction of from positive to negative, or the direction of where the positive charge will go, right? So if the positive charge is moving this way, that means the current is also this way. So now the direction of current is the same as the direction of where your charge is going. So if the charge is moving this way, that means current is this way, and then your field is into the paper. Force, field, current, right? So current is this way, field is into your paper, it will experience a force upwards, right? So as it goes this way, it will experience a force upwards, and so it will start to move up. Can you imagine? It starts to move up. But if it starts to move up, it starts to curl upwards, right? Then what happens to your current? Your current follows in the direction that it's traveling, but your field is always downwards. So if you see this, the current starts to travel and your force will start to move. So can you see that the force will just always be like this, and then you move up some more, then your force will be like this. So what you get? You will get the path that you will get. Let me change color here. The path that you get will be something like this. It will curl in a circle out of the field until it goes out of the field, right? Because the direction of the current is always in the direction of its motion, field is always in, and then the force will curl along with it. Okay, so yeah, that is the answer to this question. This is a bit of a stretch yourself kind of question, but I think it's good to know, right? Because a moving charge itself is a current. There will be a current if it's a charge moves. Okay, so your homework is worksheet 18B, question 2 to 3 for section A, and section C, question 1, on top of the questions that I gave at the end of the last lesson. Okay, great.